Good afternoon, all. Thank you for joining our today's webinar on mastering spice simulation in Altium Designer. I'm Sairam, working as a team lead EDA here at TISA Spectral Systems, other distributor for the Altium products in India. And today's session is in a recording. If anyone is having any questions during the presentation or during the demonstration, please feel free to type your question in the chat. We will discuss at the end of the our session. Now let us go ahead. Yes, here is our agenda. Just a second, just a second. Yeah, here is our agenda for today's webinar. First, we will discuss the typical painful process some hardware engineers go through using a standard approach for hardware design. And second, we will explain the need for the circuit simulation to be included in the hardware design process, help to reduce the space in typical design cycle. We will discuss where examples companies skip the simulation, where they have option and how they backfill for them. Third, we will learn about the specific advantages of circuit simulation has for anyone who wants to use it. Fourth, we'll explain the different simulation techniques, behavior, and keep your design out of trouble. Next, we will get tips on how to improve your simulation skills in design environment. And followed by demonstration, where we'll look into the circuit simulation, where you can perform. And lastly, we will close the session with the Q&A. Now let us discuss about the issues in the typical hardware design. Now first I want to do is imagine you are flying a plane and you suddenly realize that there are some critical issues with the aircraft and you didn't catch them during the pre-flight check. Now it is pretty scary to ride. You did put the testing, couldn't even let the aircraft come to the ground without making the every check possible. That would work as intended. Unfortunately, this is a situation many hardware engineers find themselves in trying to fix the problems. Again, design is already in motion. Considering the consequences of the delayed product release, they can send it for circuit simulation. That's what happened to one customer in US. They didn't spend extra weeks to simulate everything designed from the top down. They consider design to be relatively straightforward, just consisting the analog to digital converters, relays and some LEDs. It is clear that they have to simulate. It is fair that they need expert to do simulation. Unfortunately, despite the best efforts in design, few makes are made at the PC level that put them in a tough situation. Deadline in a week, but they didn't have enough time to respin new design. As a result, they will kill the project and they have lost millions of dollars funding for the year. What's unfortunate in a story like this, not as always as extreme, but still a major issue in the hardware of design cycle and electronic systems. Growing complex designs face numerous challenges when discard circuit simulation in the design process. The first is increasing the design cost. Let's look at some issues that can rise as they can result. It goes without saying that multiple hardware iterations increase the design cost. The cost of design components, designing materials, many factors, and there is delay in the project schedules. Naturally, these delays cause trigger effect as you scramble to make the necessary changes to your design. Delays impact your product time to market effect and ultimately affect your competitive edge in the industry. Design reliability and performance are also at the risk. If you don't incorporate circuit simulation in untested design, more prone to failure, which will lead to customer not satisfied and your company's reputation, which will damage your company's reputation. Furthermore, failures to simulate your design might result in non-compliance with industry standards, creating legal and financial three professions for your company. Lastly, generating simulation can lose customers' confidence on your product. And should you ever get your product, customers having problems with your product, they may lose trust and confidence on the reliability of your product. It will impact on the image, on your brand, and company's long-term success. Now to discuss about the entire thing, the need of circuit simulation in modern PCB design cannot be overstated. With electronic systems becoming more complex, designers must ensure that their designs are reliable, cost-effective, and efficient. Let's briefly explore the three key factors driving need for circuit simulation and today's electronic design landscapes, along with real-life examples, how circuit simulation can make or break your project. First, the growing complexity of the electronic system presents significant challenges in terms of design, layout, and component selection. Circuit simulation allows designers to evaluate the design, optimize the component values, and identify potential issues for they become costly problems during the prototyping phase or manufacturing phase. For example, the power system engineers field actual simulations are performed to identify potential failure points in the power grid before any construction begins. This ensures reliable and robust infrastructure. Conversely, some hardware engineers may skip the simulation step and rely on the back of napkin for linear paper calculations. These can lead to expensive and time-consuming for repetition, debugging, troubleshooting, as illustrated by simple case work 72 hours of troubleshooting to find the issue. The second is design reliability in cost consideration are critical in today's competitive market. Companies must balance the performance with the cost, and circuit simulation plays a vital role in keeping this balance. By simulating your design, you can identify the areas for the improvement, optimize the component choice, and ensure your design meets the performance and reliability criteria. Unfortunately, not everyone appreciates the importance of this circuit simulation. Take, for instance, a major company prioritize saving 12K dollars not to get simulation package and training the engineers. That was the mistake that led to extra 6 months and 150K dollars field test on the EMC and EUL certification for their product. When they found that problem, they spent extra 50K to respin the board. So here's the thing, the time to market, the product is continuing to be delayed. Circuit simulation helps accelerate the design process by enabling faster design iterations in the earliest stage of the potential issues. Not only saves time, it also reduces the cost of redesigning. The growing complexity of the electronics, reliability in cost considerations, time to market, doesn't make the circuit simulation indispensable tool in the modern designer's toolkit. By embracing the simulation, designers can avoid the costly mistake in the design with the simulation analysis. Building on the importance of circuit simulation, let us discuss the real-world scenarios and use cases. The simulation plays a crucial role in the success of the project. First, test the high-speed digital designs. These designs often involve multiple high frequencies, which can lead to significant issues and crosstalk between traces. Circuit simulation allows the designers to analyze the significantly determine the need for termination register before coming to physical design. This helps you to avoid the costly redesigns and ensure optimal performances. Next, multi-signal designs, which involve the analog and digital components, often present unique challenges. Simulation plays a vital role in understanding the complex interactions between the components in verifying entire system functions as intended. For example, designers can perform sensitivity analysis to determine the impact of the component tolerance and ADC's performance. It helps to optimize the designers and ensure accurate signal conversions. In power electronics, and high power applications, managing power dissipation, thermal performance, and efficiency is critical. Circuit simulation helps the designers to identify the areas of high power dissipation, switch losses, playback converter, and optimize the component values for improved efficiency. This not only result in better performance in design, also reduce the risk of thermal issues of the component failures. And lastly, RF circuits. RF circuits precision controls of signal frequencies and phase noises. Designs such as oscillators allow designers to access the impact of the component variations and optimize the design to keep the desired performance. Multi-color analysis particularly can be instrumental in understanding the effect of the component tolerances for a circuit behavior. As you can see, circuit simulation is essential among the wide range of applications in high-speed digital, mixed signal, power electronics, and sorry, RF designs. Incorporation the simulation into your design, you can identify the potential issues, optimize performance, and increase the reliability of the product. Now, sorry. Let us discuss the key advantages of incorporating the circuit simulation on your PCB design process. First and foremost, a circuit simulation allows the faster design iterations. By simulation, the designer can identify and address the potential issues early in the process by troubleshooting and debugging the cause. This allows you getting into faster overall design cycle. The next circuit simulation improves the design reliability. When you simulate your design, you can analyze the performance of circuit under various conditions and ensure that it will meet all necessary specifications in industry standards. This helps in avoid unexpected failures in the fields and contributes to build the reputation, reliable and high quality products for the brand in the market. Another advantage is that simplest the debugging and troubleshooting also will be a cost saving factor. By integrating the circuit simulation into your design workflow, you can create the better performance and more reliable, cost effective products. When it comes to circuit simulation, having the right technique at your fingertips is critical for tackling the diverse design challenges that comes with modern PCB designs. Today, will some popular simulation techniques uncover potential issues, optimize performance, and then bring the design into confluence. First, let's talk about the planning analysis. This power technique allows you to simulate the dynamic behavior of circuit over time by analyzing how your design responses by changing the input and various other factors. You can ensure the design performance optimally under real-world conditions. Fault analysis is an important circuit simulation technique that helps the designers to evaluate and optimize the performance of their circuit, analyzing the location of the poles and zeros of the transfer factors of circuit. Engineers can identify the potential stability issues and take the corrective actions before the circuit is built. Fault analysis helps to optimize the performance of the circuit by identifying the opportunities, improve gain in other key parameters. Next, we have AC/DC analysis. This essential tool helps to examine the steady state behavior of the circuit and both alternate current and direct current conditions. By understanding how your design operates across different current and voltage levels, you can fine tune its performance and ensure that it meets required specifications. Now let's discuss about AC/DC sweep analysis. This technique enables you to investigate the frequency response of your circuit, revealing crucial information about its stability, bandwidth, and overall performance. With sweep analysis, you can effectively identify and address the problem areas in your design. Noise analysis is another variety of simulation technique that helps you to quantify and minimize the noise in the circuit. By understanding how noise affects your design, you can make a conformed decisions to improve the security and overall performance. Parametric sweep and sensitivity analysis are essential tools explaining how the component tolerances and variations impact the performance of the design. These techniques are able to identify the critical components, optimize your design for robustness and reliability. Finally, Monte Carlo analysis. This powerful simulation method uh, use a scope method to evaluate performance of your design under wide range of component variations and operating conditions. By accessing the impacts and uncertainties on your design, you can minimize the risk and ensure consistent performance in the real world scenario. Just to mention, temporary shift can do your component to simulate the behavior of your components. Finally, the Fourier analysis is a powerful mathematical tool that commonly used in circuit simulation to analyze the frequency response of the circuit by breaking down complex waveforms into individual sinusoidal components. Engineers can better understand how a circuit can behave at different operating conditions and make more informed design decisions. Fourier analysis is used to analyze the total hormonal distortion in circuit and the transformers. We'll discuss some tips that helps you to maximize your circuit simulation. The first tip, selecting the appropriate models and components. The accuracy of simulation relies on the quality of models and the components used. We should use a website like Octopart. Ensure that you are using the up-to-date manufacturer provided models. Never possible to verify that they accurately behave to the real world scenarios. The second step is ensure the accurate parameters values are crucial for obtaining reliable simulation results. Check your component values against data sheet and manufacturer specifications. Don't be afraid to adjust them when needed to improve your design performance. And the third trick is utilize the proper simulation settings. Take the time to understand and configure the simulation settings for your design goal. Includes selecting the right analysis type, designing the appropriate input, output types, and specifying the required simulation time and frequency range. And the next tip is verify results with the measurements and empirical data. Simulation is a powerful tool. It is essential to validate results with real-time, real-world measurements and empirical data. You can add some familiar parts and unfamiliar to use the test, then test them on the breadboard or on a mini PCB, and it helps you to verify the functions as intended before moving on to the full design. This kind of steps helps to ensure your design performance as expected and enable to make informed decisions about any necessary changes for optimization. The name it again need to catch the errors early, not after the fact. The next tip is you can iterate and optimize easier and earlier during design phase. In fact, circuit simulation is an iterative process. Use the insights came from simulation to identify the area for improvement, and don't be afraid to do changes in the design and even the component as needed. This iterative process ensures that your design is robust, saving your resource and time in long run. By following these tips, and embracing the power of circuit simulation, you will be able to design PCBs that perform optimally, meeting industry standards, ultimately reaching the expectations of the customers. Effective simulation is nothing but not having the right tools, using them effectively to make more strategic designs. Now let us take a look at the how we can perform simulation inside the Altium Designer, transient, HSP, PC switch, sensitivity, multiple analysis, with the help of Altium Designer. I'm just going through Altium Designer. Yes, here is the tool, Altium Designer. Now I'm going to show you how you can perform the simulation inside the Altium Designer with some example circuits. Now let us open a circuit. This is an example circuit which I am. This is a voltage divider circuit, and I want to figure out the voltage and current at different nodes. For this, I'm going to run the operant one analysis. For this, as I see, the simulation command is available here. From this, you can able to see the other ordinal options available inside. Just click on simulation dashboard. You can choose the document or project. I just choose a document to perform the simulation. First, you need to do verification. This verification help you to identify the ERC, ethical rule check, and the simulation models are the component science spice models available or not. It will verify. And then preparation. The preparation we have got the voltage source V9. And if you want to add any voltage and current probes or power and voltage difference probes, you can add. And as I told, I want to see the voltage at the each and every nodal circuit and let's perform the operant analysis. And then the recent developments, not recent, quite long back, we can able to see the voltage and current power at the each node of the circuit by this operant analysis. Just enable these three options and just click on run. It will perform the analysis. You can see the what is the voltage. We input 10 volts. And if you go to the circuit, you can see the voltage which is over on the each node. Voltage and current values. It is 8.33 wattage and 833.3 milliampere current. And this is the voltage at this point across this point. And if you want to see any other voltage point, you can just go to sim data and you can choose the which outputs you want to analyze. You can able to see the voltages at the particular nodes. Okay. Now, this is all about how we can perform the transfer analysis. Now I want to perform the voltage analysis. It helps me to understand the stability of my circuit. I just enable this option called voltage analysis. And here I just mentioning the input node as input, output node output, 0, 0, and analysis type 0, and transfer function V output by V input. I just again run the output analysis. The same will come, but here you can see we have a voltage analysis here. Just select here and you can see the point where it will help you to identify the stability of my circuit. Okay, you can click on this here to show the values of the voltage analysis. Okay, this is how you can able to check the stability of the circuit by using the voltage analysis. Now I want to understand how output is going to change in relationship with the variable resistance in the circuit. Okay, let me close this circuit so that it will be clear enough. Yeah. For this, I'm going to perform the same on the same circuit. Here, yeah. Here, now what I'm trying to say is how the output is varying with respect to R7 variable resistor. We want to run the DC sweep analysis. Again, verification. Preparation, again the same. Now this time we want to perform the DC sweep analysis on across the R7 and output expression we want to use V output. How this output is influencing, how this value is influencing the output of circuit you want to check. Just click on the DC sweep analysis. Yes, you can see here. This is the graph. If you look at here, this side y-axis we have voltage and x-axis we have the resistance. As the resistance getting increases, the voltage drop across the resistance is getting more. You can see if we have a resistance value less than, we have a voltage of 1 volt. If we have a resistance value of 10 ohms, now the drop is around 5 volts. So this is how you have to check the voltage drop across the component by using the DC sweep analysis. Okay. Now, now we want to do another analysis by using a different circuit to understand the voltage differences to I mean to say what is the suitable value to get our required differences. This is the circuit, strain gauge circuit. Here, how is this? What is the value required to satisfy the difference between these two as 0? We want to analyze by using the DC sweep analysis. Okay. For that, Again, the same process. We want to know what is the value required to satisfy this circuit output. That's what we are trying to do. We want to determine what is the value we need to mention to make the voltage difference zero across these two nodes. For this, the same process again. Just click on start verification. Yes, we have the ERC pass and models pass. Preparation, the same V2. And here we want to have a two probes we have added. How we added, just click on voltage differences. We add the positive and negative probes here. We want to see the what is the voltage difference between these two nodes. And you can go to analysis setup. This time you want to perform the DC sweep to know the what is the value required for the R1. That's what we mentioned R1. And here also you can perform the output expression. Here I want to what is the difference between these two I want to have for this one. I want to have a new plot. Okay. And this plot I want to give a different path. Okay. Yes, now we have done this one. We're trying to understand what is the value required to make the series circuit. Again, perform the DCSP analysis. Just click on run. Yes. See, you can see we have got this is actually the voltage probes, what we have specified. This is what the expression we have created. Both values remain same, hence there is no why I have had this one. You want to see the whether I'm getting the exact results or not from the both. I want to understand. Hence I given this. Now let us delete this plot as we have not required. Delete plots. Yeah. Now this is the difference, and we want to understand what is the value of register required to satisfy the circuit. To understand where is this graph is touching zero, this is the location where it is touching zero. We will have a cursor A to touch the where it is touching zero. I think, yeah. See, this is the value. That means if you update the resistance value with 719.99 ohms, the voltage difference between the two nodes will become zero. Hence, your circuit is satisfied. This is how we can able to determine the value of the components by using the DCSP analysis. Now, previously we don't have values. We have determined the circuit values by running the analysis. Now let us say if we have the values for how the variation component values affect my circuit. Okay. For that we will open another circuit, low pass filter to perform this analysis. Now we can see we have got some generic components here. That components red color denotes the generic components. Generic components will give you a flexibility where you can quickly pick from the generic components available in the components panel, and we can go to the properties and you can be able to set the value from drop down, and you can fix your schematic capture, and later on you can able to assign the proper manufacturer information to the components by the manufacturer parts. I think you will be knowing how to add the manufacturer part information by using the manufacturer parts available in Altium. I'm not going to talk about that stuff. Now we're going to see how the component values will affect the performance of circuit by the basis web analysis. First, we will do the analysis called transit analysis for the verification purpose. Again, the same process. Sorry, we have automatically assigned the sparse modules. Preparation, we have got the three voltage sources, and if you want to add any probes, you can able to add, and you can able to. Now we are going to add and perform the transit analysis. Here we are adding the from one to and a step, and we are going to check the output expression of the V7. Now let us do the analysis. Oh yes, a second, just a second, just a second. I did this Monte Carlo is enabled HTT, which is not required, and I forgot to add a probe. What is probe? Yeah. Again, do it. Yes. These are the input. You can see for the peak to peak 1 volt. And if you see the output, there is we have a alternations and shift in the circuit. And if you look at the overall performances, there is shift in the output. Okay. Now let us on the AC speed to analyze further how it will affect the our outputs. Here we have start frequency 10 and 5K, and decimal points for is 100. And we're going to magnitude in dBs and phase you want to know, and assign the different colors. You can change the colors of the circuit, and you can able to perform. Before that, let us remove this and just perform the SSV analysis. Yes, you can see the graph, which is magnitude in dB and is a phase. And you can see here there's an increase in the phase, there's an increase in the frequency when the phase is getting decreased. And we want to this needs to be looking fine. And we have designed this filter for a cutoff frequency of 1 kilohertz. Let us see 1 kilohertz. We have the 1 kilohertz is at this point. And you can see here when the phase is getting decreased, the magnitude got increases. I think we can say it's been satisfied. If you go to SIM data, if you mention dB at -3 dB, these are where our cursor we are getting at a frequency, cutoff frequency of around 997 hertz, which is acceptable. Yes, that means this circuit also is satisfying my requirement. Like it's like working. Now I want to how sensitively my output is by varying the component values. For that, I need to perform the sensitivity analysis. Just we need to enable the sensitivity analysis here, and then expand this bit further, and let's go to settings and go to sensitivity. Here we have got two options: custom deviation and group deviations. First, we want to check the group deviations for the resistor and capacitor, and 0.10 stands for 10% tolerance and 0.2 stands for 20% tolerance. We want to perform the group deviation for the resistor and capacitors. Let's click OK, and again run the analysis. This is the sensitivity with the components values. You can see here how the output is very deviating with respect to these values. You can see. Okay. And if you look at the fifth and fourth, 9530, 9530, and first one. First 4 and 5, the resistor values remain same, but only the changes in the capacitor of C4. That means the C4 capacitor value is sensitive to our output. Okay. Now let us see only with the C4 capacitor with the custom deviation. Again, go to the simulation dashboard. Again, go to the SSP and again sensitivity. And this time we will enable custom deviation for the capacitor C4 from the product can select. Okay, click OK, and again run the analysis. So you can see here only with the capacitor values only the phase and magnitude is getting deviated. Okay, this is how we can able to perform the sensitivity analysis in the AC speed, how the component values affecting your output. Now take a look at the another example, which is buck converter. Let us say we have designed a buck converter at specific switching frequencies and specific to recycle, and we want to know what is the input voltages for these devices. So we want to know the output by using the simulation. With simulation, you can see the performance with these values. Now go to simulation dashboard, and again we will perform the same process verification preparation, V3 and V4, you can choose. If you want to add probes, you can able to code, and you can perform the transit analysis. Now we want to see the V output and RMS after the design, okay, and run the analysis. I think we have enabled different one. Yes, this time, I'm sorry, this is supposed to be 2 picofarad. Sorry. Now we should, yeah. Yes, see, this is the performance of the circuit, this is the output, and this is the RMS voltage. Okay. Now, if you take a look at this graph, you can see my RMS value supposed to be 3 volts. Okay, this is 3 volts or more. Okay, this is satisfied. And as per my boss requirement, the ripple should be 1% or lesser. Now let us see how the ripple is. For this, we will add 2 probes, cursor A, okay, and again one more cursor B. Okay, now go to sim data. You can see here, and it is 251.8 milliseconds. Okay. Okay. Now let us take a calculator to calculate the what is that voltage ripple. Okay. Now I just take calculator. We calculate by using 0.251 divided by 3 dB into 100. That means the ripple is more than 8%, which is not satisfying. Now, how we can able to adjust the ripple to less than 1%? Let us change the value of this capacitor. Instead of pico, we will say microfarad. And again, we will run the same process analysis. Okay, now let us, sorry. Just a second, just a second. Okay, just a second. Let's take it to value into micro. Yes, now. Read. Mhm. Yes, let us view this output because that is not clear. Let us view this one. Yeah. Let's take cursor A and yeah, and cursor B. Yeah, this is the one sim data. We like to use again calculator to calculate the voltage ripple 0.0028 divided by 3. Okay, divided by 3 into 100. 0.09, which is less than 1%. Hence, the our requirement is satisfied, then you can proceed further. Okay, this is how you can able to check how you are, you know, operating at different frequencies, input voltages and all. Okay, now If you look at the, suppose if you want to design the same type circuit of hundreds and thousands, then it I require the same type of components in hundreds and thousands. Maybe you get a component from market, but all the components may not be of same value. There is some kind of tolerances. How the tolerances will affect the output, you can check by the Monte Carlo analysis, which is our built with Altium. Let's go to the settings, and you can able to use the Monte Carlo analysis. What is Gaussian or uniform worst case? I can enable the component with the tolerances, and I can come down the Gaussian analysis. Okay. So this is how your output behaves with respect to different values of the components. Okay, to identify the challenges in the schematic level itself. This is all about the simulation, which help you to overcome the design challenges, the challenges in circuit performance in the design level, and you can uh, do the corrective action. And we are demonstrate the how we can perform the simulation inside the Altium Designer. Yeah. Now we are open for the questions.